So here, LLVM Code Generation Pipeline, there are three parts from a high level. So first, like machine SSA, like machine instruction selection. Machine LLVM is like loop invariant code motion. Machine like CSC is common sub expression. Sync, then peak code optimizer, dead machine instruction elimination. It's something similar to code elimination. Then register allocation, like there is this file eliminator. We are moving away from SSA, so you have to eliminate file. Then to address instruction, register coalesce or machine scheduler. There are some register allocator and virtual register rewriter, and not given in any order. So the order does not matter. So the order is not correct in this table. So then later passes like code emission. Finally, you print the ASM printer. This is high level view of LLVM Code Generation Pipeline, and this is how it is done. So LLVM Pass Manager, like you have this target pass config class, where you have add machine pass, add machine SSA optimization, tree instruction selection, ILP. I think it should be instruction level parallelism optimization, register allocation, add rewrite, add post log, add pass. These are all like target dependent passes. So for different targets, you have to write different codes. You look at target independent, like common sub expression elimination, like here is a. But if you look at LLVM IR, that will be like you can have one pass that will be applicable for all targets. But in this machine dependent, it will be like specific to that machine. There is also insert part and substitute pass available with LLVM Pass Manager. So some important classes I just briefly brush, like go through like machine instruction class. So pointer to MBB is one field. There are many fields available in the machine instruction class. You can look at the LLVM docs each and in detail later to find out what are the important fields and functions available in the machine instruction class. So pointer to MBB is MBB like machine basic block is one field. Machine basic block pointer to machine function and LLVM IR code as fields. So this very important. LLVM IR, like if you want to get a equivalent LLVM IR of a machine basic block, already a field is there, like it points to the corresponding LLVM IR code. So getting back the LLVM IR from a machine basic block is easy for the basic block. So pointer to machine function. And 5 comes as first instruction, terminator instruction like additional instructions or return instructions comes at the last instruction in the machine basic block. So machine function, it is a doubly linked list of machine basic block. So store the machine basic blocks as a doubly linked list. Then there's a pointer to IR function, target machine, etc. Again, IR function, there's a pointer. So getting back the LLVM IR from a machine specific code is easy. Machine basic block has a pointer to the LLVM IR basic block. Machine function has a pointer to the machine function. So this is a simple code where you are iterating over like a machine function, like run-on machine function. This machine function is an argument, one variable MF. So here, what you're doing is looking at the used registers. So machine basic block members in MF, machine instruction members in MBB. So each machine function consists of machine basic block, n number of machine basic block. Each machine basic block consists of say k number of machine instructions. You iterate out this, and you look at the machine operands. You get the operands. Or the operands, if it's a register, you're inserting into a set. Then target register info, like start mf code, get subtarget, gets register info, then print rich TRI. This prints the registers that are used in that machine function. So again, this there are calls again. This pass, which runs on the machine function, it calls this API like get subtarget, get register info. Class assigned is target register info. So there are, as you have seen in the previous LLVM tutorial, also there are like lot of LLVM classes. Going through all the classes, so even knowing all the classes will be tough. Use it as an educate. That's all you do. So to write machine function pass that use like this initialize pass, like you might have seen in LLVM IR. Initialize pass, my pass, debug type, your pass name, then some other arguments. So then run on machine function. If it is function has this skip function, skip this function, skip. Otherwise, you do the work and return true. So this initialize my pass is the way you write this virtual. Sorry, this LLVM pass. So any queries on this?
Yes, I have a question. So
Sure.
let's take the example. I mean, we usually assume that we have an exact processor, right?
Yeah.
What if we have an approximate processor? For example, I guess we know already that multiplication is very expensive.
Yeah.
What if I gave you a processor which can compute multiplications much more cheaply, but it will be approximate? It will not be exact. So is there any way to pass this kind of information about a particular instruction via this framework?
This the thing is it's like here, like this project transform info, like can give an answer of each instruction, like what is the instruction cost, what is like this. I gave an example like UI to FP 8 instruction, how many machine instruction for this, like there is a target specific information available in this target transform info. Available in the sense, once you have a target, you have to fill the or write all the codes here. Like, so for that target, so for each instruction will be a, for example, there will be a field like how many clock cycles are required, what is the addressing mode, what are the number of operands. There are so many fields. So those things, once you have that, then using this API, you should be able to provide such information. That's what my understanding was. Like get instruction, there's like get call instruction cost. So here there is get instruction size in bytes. So there are so many functions like exact functions and dot. But look at the Oxygen LLVM Oxygen, where you will find exact details about API functions available, and you can add your own functions and within the class and incorporate. So it's about how you implement. Like once you understand the target, then once you have the entire data sheet of the target, you analyze the target, then have a comparison, then implement all the target specific details. Then you write a pass. But fill this target instruction info. Instruction info is one of the class where you can have information about instruction. Transformation information like this, not just specific to instruction, like cache line size. Please, Clear?
Yeah. Okay. And yeah, there's one more question. So I don't know if you're familiar with the Itanium architecture, but one of the problems that we saw with majorly these kind why we don't have VLIW processors and Itanium successful today is because they said that these instructions in order to give to the processor. Now, what I see here is that you do have very good conception of basic blocks and you do have very good conception of instruction reordering. I still do not understand fully why it was very hard to pack instructions enough for the Itanium processors to take advantage of the good amount of parallelism in there.
Yeah. Titanium has VLAW like a vector processor or that's the question. Or?
Itanium was this thing known as EPIC, explicitly parallel instruction computing.
I'm not sure about it because not very expert in this backend things, but so what are the typical? I would like to know what are the typical how this parallelism is provided, like how the instructions, like how parallelism is available, like how it makes it parallel with using the machine instructions of parallelism achieved. Like typically you expect a VLAW architecture or a multi-core machine.
Yes.
So here Titanium is in which category? Like I'm telling with respect to Prince taxonomy or
so Itanium was like the middle ground between a VLIW and a uniprocessor. Like what they basically said was that, okay, so in x86 you have this really complex decode stage, right? The decodes your instruction into multiple micro ops. Now what they said was that, okay, we are not going to have this CISC style of doing things. We're going to give these micro ops to the compiler itself, and we assume that the compiler will extract enough parallelism from these micro ops and package them into good basic blocks and give us the basic blocks to execute, which the processor was designed to be really good at. Now, that is where my doubt is, that we have so much facility to do exactly this thing, then why wasn't it done? I mean, there's obviously one part of the puzzle that I'm missing here.
This I'm not sure about. With this is a very target specific question, so I'm not sure. But so have you done any reading on it or like any? I'm not sure. Like because there is parallelism available in instruction reordering is possible. Whether any target specific reasons are there, I'm not sure. Like you're asking this or you explore it or any clues?
No, I mean, yeah, just general reading. This is all on Wikipedia. There's nothing specific in this.
Okay. Like I'll explore and find out because mentioned like here this I would like to say is this backend have this much like process. These are not just entire set and not in any order. So and what I told like instruction like reordering instructions in a basic block, they're like well-known strategies. But not sure. I will maybe explore and get back.
Thank you.
Because I'm not fully sure about it. So basic understanding had to be at when here is that there is target specific classes available in the LLVM where you have to fill with appropriate code, and like typically I related it to a device driver type of thing where you have a specific set of operations like open, read, write. Here it's a bit more complex because different instruction sets, different architecture as mentioned like VLIW and even superscalar. There are so many things. So so that way it's a little more complicated. So each specific target, expertise in that target architecture is required before you write the code. then the passes how it should handle. Like that is also tricky. Like you may have to write your own passes for that specific architecture. So thing is, here there is LLVM table gen, like which can be used to give information about the specific architecture. I'm not going to cover it in detail, but the time being, I'll just give a look at. I'll just share terminal. This folder, like is visible, this terminal. Terminal is visible, right?
Yes, sir.
Yeah. So I want to mention is here, if you look at the lib, this is the target, like LLVM source, lib target. So you can find so many targets in this thing, like AR64, AMD GPU, then this NVPTX, MSP, MIPS. MIPS, like typically you use for is done typically for MIPS is one of the architecture that is typically used for academic courses where you can cover it in 6 months. So there are so many other architectures. So you can find target instruction intrinsic info, this instruction info. You go to AR64. So this there are a lot of functions, like I should say this target machine.cpp, target transform info.cpp. The table and file where you can find details about the architecture instruction set.
There's one question here. So
Yeah.
I think AMD's latest instruction set, I think V8.3 or 4 has this thing called Neon, in which they provide support for vectorized instructions which can be dynamic. So the problem generally with vector instructions is that you have to specify the width of the vector, right? You have to specify 64 bits, 128 or 256. This Neon ISA, it has this capability to dynamically scale the vectors on the basis of available operands. Now, any ideas on how it does that?
No idea. Like the thing is, what I would like to is basically my expertise, or my most of the work have been in this LLVM IR process where you transform codes, instrument the code, do control for analysis, data for analysis, and adding metadata, those things, and target code generation or the target specific implementation with respect to LLVM. I'm not an expert, but yes, all architecture are independent, but and you have to know the exact architecture. Cannot comment, but I can understand that this vector instructions, if it is say number of operands is say you are having an addition where it's like say 12 vector size is 12, like
Not implemented in the microarchitecture. So it is somewhere, it is operating in one of these passes, but I don't know where. But yeah.
Yeah. So the thing is, Even I'll show you one of the reference videos where you can find details about this. It's possible to print the LLVM MI machine intermediate code. I'll just show you this example. So, one minute. So we generated this main.ll. Then we can. So you have been writing this LLVM optimization process using op2, but here you can have LLC using LLC and print the MIR machine intermediate code. So, here we have this main.mir where it's generating the code for MIR, like and you can pass this LLC like in a stop after passes, where you can give a specific pass related to the architecture. If you look at that LLC command line options, you can find that you can have a stop a MIR code generation before or after a pass. You can even run a MIR. You can take a input MIR and run a pass, then generate a new MIR. So this way you can try running on this LLVM MIR and do some small, write some small passes on LLVM MIR, like small optimizations. Say to start with, like people optimization, like small optimization. You give a corresponding input, and you can check whether this MIR pass are working and how to slowly you can learn. Then after that, so what is the avoid mirroring. Yeah, so yeah, so so here you can do this LLC command to something similar to op command that is used for LLVM Midland IR or IR passes. You can use LLC to simplify MIR. Then you can take a input MIR, can run a pass, like, and the pass you can give like a stop after, and so if you have written your own pass, you can give that your pass name. Then corresponding argument like LLC, and check whether your pass are running. So whether it's specific to, since it's maybe specific to an architecture, you have to specify the architecture like MRX 6664. So the using this LLC can write your own passes, test things are working, and modify the backend code generation. The way you draw LLVM passes on IR, where you transform one IR to another IR, like input the LLVM path may be IR1, input output will be IR2, but they're going to be semantically equivalent in almost all cases. So, so here you can take one MIR, you can run a pass, modify to another MIR, preserving semantical equivalence, semantically equivalent MIR, modified MIR. By writing your pass, like you have to get the LLVM doxygen and stopping presentation. So LLVM doxygen has enough documentation for all these classes, like even all the classes, the same way as we have done for LLVM midline passes, like whether it's instruction class or value class, and mesh basic block class, function class, what are the API functions available, how it can be done, we have seen. In a similar way, for this, you can use for this backend code generation the doxy and what are the classes available in the LLVM for code generation. So the target transform info class, machine basic block class, machine instruction class. There are some basics, elementary classes. Once you go through that, you'll find so many other classes, and if you know it, yeah.
No, you're not presenting right now, right?
Yeah, not presenting. Yeah.
Okay, fine.
And so if you know any one specific architecture, like MIPS or anything, and you may find like how things are working, or even AMD, or like you can look at the target specific classes, because this is target dependent. Unless you know the target, it may be difficult to understand the code. So, as I mentioned in lib analysis, the target folder, there are different targets available. There is like AMD GPU, NVT PTX, like NVPTX, that is for GPU. These things are available. You can look at that codes and find out how things are working. Unless you are not familiar with the hardware, it may be tough to understand. So TableGen is like a tool for specifying the details about the hardware. Like each inspection has its own properties, like clock cycle, what is the instruction name, what are the operands, whether it is having any side effects. There are so many details. This LLVM TableGen has lot of other details, like it comes as takes a input and generates a detailed output, like comes like a DSL. So in the interest of time, I'm not covering, and maybe I can. One thing I suggest all of you is to look at the subscribe to the LLVM public videos. There you will find a lot of interesting videos, and even for my lecture, I referred 2 videos for LLVM from the LLVM developer community. That lot of information is available, where target specific information for classes, target specific lectures are available. That may be helpful. So just to brief upon, like maybe I'll just share the so like here, this much things are there in the backend, like machine SSA, optimized visualization, like it starts with file elimination. So SSA form is not maintained. Then later you print the assembly code using ASM print. So the optimization, again, just basic example. And it's like instruction selection and even liveness analysis is still in SSA form after registrar location, not in SSA. Then IR versus MIR. So then this, so each architecture has its own implementation about implementation of the LLVM classes, like target instruction info, target transform class. So those each architecture has its own implementation that is specific to that architecture. If you are familiar with any of the architecture, you can go through that code. It's already available in the LLVM source directory, that lib target directory. So this machine dependent optimizations are possible. So that is done. What is already there, what extra you can add, constraints that you can look at. So the instruction info target transform info, you have LLVM pass, that is the back code gen pass. So I got two questions. One was related to titanium architecture and why there is no support for this parallel implementation, and what is the other question I didn't answer. I look at it and update.
So, I have one doubt regarding that. You talked about that we can access the IR from the MIR from the directory, right?
Yeah.
There is some pointer. So, where is the thing being used? Like when we get back from MIR to IR?
IR to IR, where it is useful. A question to answer that question, like when you need traverse back like a machine IR, but explicitly not sure about where it is required, but I mentioned that things are available. So reverting back to the MIR to IR is easy. And exactly where it is used, not give a specific example.
I have another question.
Yeah.
So let's say that you have compiled a binary for a target, right? You've converted the MIR to the assembly. Now, when we think of cross compilation, what we generally say is that I'm going to need the source code, and instead of compiling from MIR to x86, I'll instead compile from MIR to, let's say, ARM.
Yeah.
But MIR to x86 is not, I mean, can we go from x86 to MIR and from MIR to ARM? Like, is it possible to reverse this conversion process from the assembly to the MIR?
Assembly, I'm not sure, but MIR to from MIR is possible, like MIR to IR, and then reverting back is possible. But I'm not sure with assembly, x86 assembly cross compilation. I think it should be there, but I cannot accept. So cross compilation is a well-known method. Like, so whether you should convert from MIR to the different architecture. Like once you have MIR, you can get back the LLVM IR, and from LLVM IR you can generate code for any architecture. So that is not an issue. So from assembly, not specifically looked into it. That's all I want to say. So that
Sure.
may require,
Thank you.
it may require from assembly. So reverting back, as far as you have data structures to maintain such MIR to IR assembly mapping, would be okay with it. So cross compilation is a well-known concept, right? So support should be there. Exactly how and all, I don't know.
Yeah, and is there, like, generally we consider the size of code to be quite important. So is there any idea of what is the code expansion factors for different targets, or like how much does the code expand when we go from IR to MIR?
Yeah, that's what. Like it depends on the like this architecture dependent things are there, right? For example, the floating point example, UATFT, like if it is based on the architecture being supported, like whether it supports the full floating point, full floating point 16 is possible, right? Because it's like it expands, and also you have this. Suppose you have a for loop, and you know this loop unrolling for better parallelism. The instructions are to have this pipeline to be full. In that case, some cases you by default increase the number of instructions to an extent so that enough instruction level parallelism is there. Some places you may have hardware support for having one instruction, but some places you may not have support, like this example. With full FP16 you need only one, and without FP16 you need only this much instruction. So, and some places this loop unrolling and those concepts for instruction level parallelism. Right? So there to increase the instruction by as compiler optimization, it is done. So to have the instruction level parallelism on the higher side. Does it answer your question?
Yeah. Okay. I mean, I was looking for a number, but I guess it's very hard to give a number directly. So yeah. Thank you.
It's like depends on the architecture as I mentioned here. Like if there's no support, for example, if there's a vector instruction available, then save a lot of instructions, right? Number of instructions, but then how many, like performance and all, there are a lot of dependencies like cache size, number of registers, so many architecture dependent factors. So it's very tough to mention a number. So I hope this lecture will motivate you to subscribe to this LLVM developer community YouTube channel. This YouTube video, there are a lot of videos. I referred two videos, and like even TableGen also I looked into, but much of time I didn't. So there are a lot of videos available, like this, like 2019 LLVM developers make 2017 LLVM. So it will be good if you look at subscribe to like look at some interesting videos for your future opportunity. First half I have referred the compiler design, drag and book the house at your like, just to give the importance of register location and liveness analysis. Global register location. Even for how to remove the temporary variables for expectancy. Also, yeah, this chat box, there is this LLVM MCA mentioned.
There's one
It's
more
like
question, but
yeah, this
yeah,
LLVM
sorry.
I want to mention like the reverse engineering is like what typically each inside. Yeah. Please ask the question.
Sure. So we talked about instruction reordering, right?
Yeah.
It turns out that there's one more place where we do instruction reordering, and that is in the processor when we execute these instructions in an out of order fashion.
Yeah.
So do both of these are both of these processes aware of each other? Do I reschedule my instructions in the compiler in order to extract more performance from the out of order execution? Is that possible?
So that depends, like as I mentioned, if it is say at the end, instructional parallelism should be achieved through the hardware, but this software pipelining is there, like hardware pipelining is there. So from the hardware side also, like from the software side also, it's okay.